we're moving slowly towards the end of the conference. We still have one talk, and then the closing keynote, and then the apéro, and then flying dinner. But first, we have Dagmawi Mulugeta from Netscope. As I previously mentioned, I met Dagmawi this summer at Area 41 in Zurich when he was looking at the attack side of it. And we always tried with Cyberstorm to have takeaway messages or present solutions. Like, yeah, it's good to know that everybody's vulnerable, but we knew this before. But are there also ways to protect ourselves? Do you have ideas how to prevent the command and control structure be hiding itself in Outlook or O365 traffic, Dropbox traffic, or whatever? And say, yeah, actually, I'm researching this summer, and he told me he was confident he'd be ready by October, and it's like, yeah, you're booked. Because that is really a topic that is very important for, I'm sure, a lot of the audience, because you have big networks, you have probably hundreds or thousands of clients, and you have a lot of encrypted traffic, and you don't really know what's happening. So I'm very happy that the research was successful, and I present you Dagmawi Mulugeta.
Awesome. Awesome. Thank you, Christian, for that wonderful introduction. I'm so happy to be here at Swiss Cyberstorm. One of the benefits of being a speaker at a conference is you get to attend all the other amazing talks as well. So I've been jotting down my notes on all the other great talks we've had here. I hope that this is up to par with the caliber of what we've seen today, but I'll let you guys be the judge of that. So let me get started by introducing myself. My name is Dagmawi Mulugeta. I am a threat researcher at Netscope Threat Labs, and today I'm going to be talking about how to detect a specific attack technique called cloud command and control. So let's get started. So the outline for this talk is as follows. I try to always have like a set route so that everyone can kind of follow along as I ramble on, right? We're going to start out by defining what Cloud C2 is. What do we mean by cloud command and control? Is it happening? How is it different from traditional command and control? And then we'll go over why is this hard to detect with the existing controls? Why can't, you know, the things we have now just detect this additional thing as well? We'll take a little bit of a kind of deviation a little bit to talk about our lab environment and how we collected the data that we're going to use to present the meat of this slide, which is our detection approach. How can we detect Cloud C2? And we'll present a relatively new way of attacking this technique or defending against this technique, and we'll finish it off with a quick demonstration of how we can implement this in a quick Python script so we can actually see it work, you know, put the tires to the road and kind of see the detection kick off. So let's get started. So what do we mean when we say Cloud C2? Let's start there, right? So before we get into Cloud C2, however, we need to talk about command and control. So command and control, for the maybe one or two people here that aren't familiar with it, is a stage in the cyber kill chain. Typically, it's the cyber kill chain is a set of steps an attacker uses when they compromise a target system, right? It typically starts off with some reconnaissance to gather information that they'll use to find a weakness. Then they'll use this weakness to weaponize a payload. I'm talking about the attackers, right? They'll weaponize a payload, deliver that to the target system that will exploit the weakness that we found, and then a particular piece of malware is installed on the target system. And you can see this in the diagram, right? Once this malware is installed, it's going to phone back home and pull for additional commands. So this network communication where they're pulling, the malware is pulling for additional commands, executing them, returning the results is what we refer to as command and control traffic. Traditionally, it has been done via mediums like HTTPS and DNS directly to the attacker-controlled server. And if you wanted to simulate this, you know, there's a variety of frameworks out here. Most popular one is probably Cobalt Strike that you can use to, you know, simulate this technique. So what do we mean when we say cloud command and control now, right? What is that? How is that different from what we just talked about? So traditional C2 is where an attacker, you can see this on the top right, is where an attacker will set up their own infrastructure. They'll set up their own servers, their own domains, et cetera. And a compromised device is going to reach out to this infrastructure for its commands, then upload the results, maybe do some data exfiltration here as well, right? So this is a more traditional type of setup. Now, this has been tough to detect in the past, but the security community has done a pretty good job of using threat intelligence feeds, IP and domain-based block lists to identify these servers, block them, right? A security researcher will see that a particular piece of malware is communicating out to these IP addresses. They'll send that to an IP block list. Other security researchers will pull that down and use that to prevent, security individuals will pull that down, prevent communication to those servers. What attackers have what attackers have done more of in the last few years is they started abusing cloud applications as a medium to send these command and control, or send these commands and then pull these results back. So they're using things like Dropbox, Google Drive, Slack channels, S3 buckets to send their commands to compromised devices, and compromised devices are going to send these results to cloud applications, right? Why would they want to do this? Well, firstly, it's very minimal setup, right? And that's why everyone uses it. It's quick to kind of get set up and get going. It's very cost efficient. Oftentimes, there is a free tier in these cloud applications, so it's probably not going to cost them a whole lot. And if you're trying to blend in with existing traffic that's coming out of a network, you have a better chance of using Google Drive, because a lot of people probably use Google Drive in that corporation already, right? So there's this incentivized kind of move to abusing cloud applications. So how often is this really happening, really? So in this slide, it's a little bit of a noisy slide, but what I wanted to show is the malware samples and the cloud apps they've abused. So you can see Boxcon, Nimble Mamba, and Crutch have abused Dropbox. We've seen Graphite and Blue Light have abused OneDrive. We've seen Slack abuse, GitHub abuse, Google Drive, Twitter, Tumblr, Blogspot, Google Docs, Google Script, Pastebin, OneHub, Telegram, Microsoft Teams, right? All of these cloud apps have been abused for command and control. And as you can see, there's really no cloud app that's immune to this, right? Either the threat actors have abused them, or they will continue, or they will abuse them in the future, right? You can't say, oh, my corporation doesn't use this cloud app, so I'm probably okay. It's probably coming. So, and this is a select list. There's a much more detailed list that's up on MITRE's page. So this is an issue that's actually happening right now. Okay, so we defined what Cloud C2 is. It's command and control traffic abusing a cloud app. Why can't my existing controls identify this, right? It's command and control traffic. So in this slide, we have a screen cap from a tool called Fiddler. So Fiddler is maybe those of you that aren't familiar, it's a web proxy that lets you log network requests that are going out of your system. So we have two processes running here. In the top, the first part, you can see it's the GitHub desktop app. So this is the actual valid GitHub executable downloaded from GitHub site. And the bottom is a malicious payload from a tool called C3 that's called a relay that's abusing GitHub for command and control. So benign traffic and malicious Cloud C2 traffic. And you can see both of these traffic patterns are going to the same domain, right? api.github.com. This domain is a valid cloud provider domain, and the traffic to this domain is encrypted using the cloud provider certificate, right? So an IP and a domain-based block list isn't going to be as effective here because it's GitHub servers, right? You can't block out GitHub, or else your corporation might not function correctly. So you need a new way of detecting this, right? So before we get into our detection approach, let's talk a little bit about our lab environment and how we got set up to collect the data and reach the conclusions that we've reached. So we use a lot of tools in our research, but the three primarily that we want to call out are Empire, C3, and Fiddler. So Empire is, that we kind of talked about in the beginning, is a PowerShell and Python 3 post-exploitation framework. So it's open source. It's a tool to kind of quickly get set up and simulate some C2 traffic. And if you guys haven't used it, I highly recommend it. It's a great tool to kind of play around with as well. C3 is similar to Empire, but it's more focused on providing a large medium of cloud apps to send your commands through. So it has over 10 cloud apps that you can abuse to send your command and control traffic through. And it integrates with tools like Cobalt Strike and Covenant to allow you to, get that functionality. And then lastly is Fiddler. So Fiddler is a more defensive tool than the first two. It's a web debugging proxy that gave us insight to the HTTPS traffic from a machine, right? So we're kind of decrypting that communication, logging it so that we can see what the network requests are going out of a system. Awesome. So what does a typical lab machine look like? So you can see here we had 3 types of processes running, right? If we categorize them. We had normal browsing, right? So we had Chrome, Firefox, etc., visiting these cloud apps like how a normal user would, generating that normal traffic. We also had these native apps, what we call sync clients installed. So these are like the GitHub app, the Slack app itself, the Google Drive app that we had installed on these lab machines to generate that normal traffic. And then we also had malicious processes, so C3 and Empire payloads that were running to generate this malicious Cloud C2 traffic. So we had normal benign traffic that was generated from these browsers and cloud applications, and then we had the malicious traffic that was generated from Empire and C3. All this traffic is going through, I should say going through this way, through Fiddler, that was decrypting, logging all of these requests so that we could understand all the communication that was happening here, right? We exported it out as a .acz file for analysis. Awesome. So let's bring everything we just said together into one slide, right? So we had our lab machines. They're generating traffic, malicious and benign. Together, we're going to refer to it as inline traffic, right? So it was generating inline traffic. And we're going to use that inline traffic to extract a set of signals, right? Those set of signals we're going to extract are basically categorized into 5 groups. The first group is beaconing signals. So this is going to tell us if we see any kind of beaconing patterns that are present in the traffic. The second set of signals are anomalies, right? So do we see anything that's different from what we come to understand about this user in this organization? The third set of signals are content, right? What kind of content is being used? Is this normal ASCII readable text, or is this encrypted and encoded data that's being sent? The fourth, are there any strange host access patterns that might be present that we want to make a note of and use to identify possible malicious behavior? And then lastly, are there sequences here? Are there any kind of repeated patterns that a robot would make, a normal human browsing wouldn't actually generate? So we're going to use these 5 categories of signals, and we're going to pass them through a threshold-based test, right? So we're going to pass them into the head with the gear that's then going to decide, is this benign cloud traffic, in which case it's allowed, or is this malicious Cloud C2 traffic, in which case it's blocked, right? That's essentially what our detection approach is. We're going to get this inline traffic, extract these signals, use it to make a decision that's then going to say, this is benign traffic, or is this malicious Cloud C2 traffic? So what are these signals we're going to use? So our beaconing set of signals. So in this screen cap, again, we have Fiddler. And the top is Dropbox being abused by Empire, and the bottom is GitHub being abused by C3. So 2 different tools abusing 2 different cloud apps. So we can see there's a similar set of patterns here as well. Here though, right? First is there's frequent checks to the same URL over and over again, right? Repeated checks. We can see that there's a repeated request and response pattern. There's a 409 on a GET request at the top, and then a 200 on a GET request at the bottom, right? There's an unusual process making these requests. This isn't a browser or the native app. It's something else that's making these requests. And there's not much deviation in the data that's being sent, right? That's being received from these servers, right? So it's obviously these repeated checks to see if there are any new commands. So if we see these patterns appear in this traffic, we're going to extract these signals, and they're going to tell us if we see any beaconing that might be present. Second are any anomalousness that might be present in the traffic. Again, the top is Empire abusing Dropbox, and the bottom is GitHub being abused by C3. You can see the first set of signals are there any unusual cloud entities being used, right? So when you say entities, these are the components that are specific to the cloud application. So things like Slack channels, GitHub repos, Dropbox folders, right, that are strange for this user or this organization. Second is, are there any unusual user agents that might be present? So typically, malware authors are going to take a user agent that's most popular at that given time and put it in the payload, and that's what they're going to use. But that might be different from what the user uses, right? So if we see that, that's something we want to make a note of as well. Thirdly, are there any unusual usernames being used to log into the app, right? So typically, a corporate user is going to have their corporate email, maybe one or two other usernames that they use to log into the app. If we see a new username that we've never seen before, that might be something we want to make a note of as well. And then lastly, if we see an unusual authentication method. So typically, these large organizations use SSO or an IDP to log into these cloud applications. If you now see communication that uses a bearer token in the header, that's something we want to make a note of as well. And one thing I forgot to mention is none of these signals by themselves are inherently malicious, but what we can do is we can use all of these signals together to make a more informed decision. So that's kind of where we're going to go with this. If anybody's saying, well, unusual user agent is malicious, it's not. But when all of these patterns are present, that's when we can make a really accurate decision. The third set of signals are the content, right? So what is the content here? Is it encrypted or encoded? On the right side, as an attacker, attacker using GitHub for command and control, right? So you can see that the attacker is encrypting and encoding the content, putting it in a repository. Victim's going to pull it down, execute those commands, upload the data in encrypted and encoded fashion as well. Similar process for Dropbox, encrypted and encoded text file. So if we see the data that's being sent is not human legible, it's likely encrypted and encoded, that's something we want to make a note of as well. And then the last two were actually discovered by F-Secure. So F-Secure is a team that developed C3, which is a tool that we heavily utilized in our research. So got to give credit where credit's due. They did a really good job. But they noted a few things that we want to call out as well on how to detect this. Firstly, if you don't use Slack and you see communication with Slack.com, you want to flag that, right? That's kind of obvious. Second is a lot of the communication to these cloud providers doesn't have refer in the header, right? It's not refer traffic because this malware, the malware is just going to reach out to the same set of endpoints over and over again, right? But human browsing, it's a lot of clicking and it's a lot of reaching out that we want to flag. For the third set of signals is the different set of domains that that the app reaches out to. So in the Slack app, you can see at the bottom, it reaches out to a variety of domains, not just Slack.com. It needs to get CDN content, avatars, GIFs, etc. So it reaches out to a bunch of other places. But the malware payload that's abusing Slack only reaches out to two domains, Slack.com and files.slack.com. Right? So that's something we want to see as well. Like how many other domains is this process reaching out to? And then lastly, our sequences. What sort of sequences are present here that might be indicative of more robotic type of behavior? So if you see any known hard-coded endpoints and you see a spike in those, that's something you want to flag, right? So malware authors only use a certain set of APIs. If you see those APIs being used in a high amount, you want to flag that. But also if you see certain sequences that are present, right? So a download followed by a delete followed by upload over and over again is not really human browsing behavior, right? So if you see that, we want to make a note of that as well, right? So we're going to make a note of all of these things. Okay, so we talked about a lot of signals. And the proof of concept that's kind of going to follow the slides following this, we want to kind of point out that, or we're going to say that we're going to use a select few to kind of make our decision. And the ones that we used are listed out in this slide, right? So the first is if we see a low number of domains being contacted, we want to flag that. If there's a low number of referred traffic, we want to flag that as well. If there's a spike in known Cloud C2 domains, is the data encrypted or encoded? Is there deviation between these requests, right? The interval between the requests, is that deviating or is it every second? Right? Is there an unusual authentication method, unusual user agent, repo, username, Slack channel, bots, apps, etc.? That's something you want to flag as well. So what are we going to do with all of these signals, right? What we're going to do for this proof of concept is going to pass them through what we call a threshold-based test. In our analysis in this proof of concept, what this really means is if we see more than 5 of these for any process domain pair, we're just going to flag it. Ideally, in the real world, you want to use some sort of decision tree, some sort of robust statistical analysis tool for this. But for the sake of starting out, we're just going to use this threshold-based test, right? So if we revisit what we're going to do, we're getting all this inline traffic. We're going to extract a set of signals. We're going to see if more than 5 of these signals are present. If so, it's likely malicious Cloud C2. If not, we're going to see this is benign and pass it. Awesome. So let's hit this quick demo. So we're going to look at 3 brief examples. The first is Empire abusing Dropbox. So Empire server is going to upload those commands to Dropbox. The victim's going to pull them down, execute them, upload those results back to Dropbox for the attacker, right? So we gathered data for this for, I believe, about a day, and we're going to see if we can identify this Cloud C2 communication. Awesome. So you can see here we have this script running, but it has 4,000 sessions in this file. That's 4,000 process to domain communications for the entire day. And it's going to take a second to load, but we're going to try and see if we can identify the Cloud C2 communication here. Okay, so you can see a lot of this traffic is the browser reaching out to a variety of endpoints. But you can see we flagged one particular session as likely Cloud C2, right? And if we take a look at that a little bit more, you can see it's a PowerShell process talking to a Dropbox endpoint that we flagged as likely Cloud C2. And if we take a look at the reasons why we flagged this, you can see it's firstly sending 860-something requests to only 2 domains, right? None of this traffic is referred. The authentication method being used is a bearer token, right? The content is encrypted. The time interval between requests is 2 seconds with almost no deviation. The user agent being used is unusual for this user, and it sent requests to 2 endpoints that are known associated with Cloud C2, right? And because of these indicators, we're flagging this as likely cloud command and control communication. And if we repeat this process for C3 abusing GitHub, we get a very similar result. So C3 here, different tool, different cloud app. It's going to push those commands up to the GitHub repository, right? The victim's going to pull those commands down, execute those commands, upload those results to GitHub. The attacker is going to pull them down and show it, right? So you can see, in this case, we flagged 2 sessions as likely Cloud C2. The first, if we look at the indicators, it sent over 600 requests to only 2 domains, right? None of the traffic is referred. The content is base64 encoded. The time interval between the requests is about 5 seconds with almost a 2-second standard deviation. And this is interesting, right? It's communication with unusual repos. So there was a slew of repositories here that we hadn't seen for the entire organizations that were being used, right? And because of this, we'll raise this indicator as well. And then lastly, we saw an unusual username being used here as well, right? So this insider threat 648 is something we made up that no one in the organization uses. So because of that, we're going to flag this as well. And this, I believe, was for api.github.com. The second session was to raw github-user-content.com, right? So 2 domains that this malware payload was abusing, they both were flagged as Cloud C2. Similar set of reasoning there as well. And then lastly is C3 abusing Slack. So same tool, but a different cloud app, trying to see if we can identify this particular session. You can see it had over 1,000 requests, only 2 domains. None of the traffic was referred. Bearer token for the header. Content is encrypted and encoded in this case, right? The time interval is about 5 seconds, 2-second deviation. We see unusual usernames here, so the Slack doesn't actually use the username in the session, it uses an ID. Right? We saw an unusual set of channels, so you can see like this hacking channel and a bunch of other ones as well. Unusual unusual apps, unusual bots, and you can see that it sent requests to 7 known domains associated with Cloud C2, right? So because of all these indicators, we flagged this as likely Cloud C2. Awesome. So let's go back 50 steps back to when we started, and we had this outline, right? And we talked about what we're going to cover in this talk. We started out by saying, what is Cloud C2? We defined this as command and control that's abusing a cloud application. We saw that it's different from traditional C2 and that it is happening, right? A lot of threat actors are abusing cloud apps for this. Then we talked about why this is hard to detect, right? Why existing controls can't identify this. And this because the C2 traffic is going to the valid cloud provider servers, right? That's going to Slack servers and GitHub servers. Then we introduced a potential new way of approaching this detection problem that's using behavior-based signals to identify the C2 traffic, right? And then we saw that we can quickly take a select set of these signals, write up a quick Python script that we can use to use these signals to identify this Cloud C2, right? So we kind of ended on that demo. Awesome. So I'll be taking questions in just a second, but this is my details in case I don't get to your question or you just want to talk cybersecurity, my Twitter, my LinkedIn, and our blog where we have a bunch of other cool cloud stuff. Aside of that, awesome. Thank you.
Wonderful.